Luckily, I have an extra one. Next time, you get some sleep last night. You know, this weekend you get an extra hour of sleep.
You went to room?
What was
it?
Like, all night.
Was Saturday or Sunday?
Saturday night. All back. Sunday, you get an extra hour. All right, so we're going to continue with functions today. This is the slide we left off on. So we're going to start off first with the difference between when a function is increasing, decreasing, and they like to mix that in with the questions about whether a function is positive or negative. So let's start off with increasing and decreasing. You should have seen this a little bit in Algebra 1. When you use the words increasing or decreasing, you always assume that you are going along the function from left to right. So as you travel from left to right, if you are also going up, then your function is increasing. If as you go from left to right, the function is going down, then you are decreasing. And if you stay flat, then it's called constant. Your function is constant. So what happens is now when we start changing direction, when we have these turning points, there's going to be small intervals where, like, watch, as you follow my pen. Right now, am I increasing or decreasing? Increasing, but then I might turn around and then I'll be decreasing, but then I'll turn around and then I'll be increasing and decreasing and increasing. And every time you have a turning point is when your function changes from increasing to decreasing. Now, here on these examples, these don't have any changes of directions. So this first example here is only increasing. As you go from left to right, you're also going up. The second example is what? Increasing. And then the third example is, I should have just said it in that point. I said it. Wait, I did it again. If you're neither increasing or decreasing. Now, the questions that I'd love to get mixed in with these, right, so that to make sure that you can differentiate between the two, is now not asking whether the function is increasing or decreasing, but whether the function is positive or negative. What acts as a line of demarcation between whether a function is positive or negative? Let me rephrase that. Let me take a step back. Which variable means function? Like when I say a function f of x, what variable am I representing? The y, right? So when I talk about the value of the function, the value of the output, I'm talking about the y, like what the function is outputting. What line determines whether y is positive or negative? Well, the x-axis. Yeah, I ran out. So when the verbiage changes and they're asking you not if a function is increasing or decreasing, we want to know where we are relative to the x-axis. So like on this first example here, yes, at this point where I have my pen now, I'm increasing, but what is the value of the function? It starts with an n and ends with a negative. Yeah, I'm increasing, but I'm still negative. I'm still negative, I'm still negative. And then I find the value of the function finally becomes positive once I cross the x-axis. On the second one here, yes, I'm decreasing and I continue to decrease, but what's the value of the function? Yeah, the function is positive. Eventually, once I cross, I become negative. What we're building up to is the ability now, once the function starts doing this, to be able to determine, okay, on which intervals is the function increasing, on which intervals is the function decreasing, on which intervals is the function positive, on which intervals is the function negative. Okay, meaning that it's going to change throughout. So here we go. Let's looks like the first example here is an upside down parabola. And they want to know, is this increasing or decreasing? Well, a parabola has a change of direction, a turning point. What did we call that before? We haven't really talked about it too much in Algebra 2, but in Algebra 1 you got a lot of this. What do you call the turning point of a parabola? Oh, very good. It's the vertex, sure. And then now once a function starts having multiple turning points, we can just call them turning points, or what are also called local maxes or mins. You see how this one, this is a cubic function. This has two turning points. Okay. On a turning point, your function goes from increasing to decreasing. A turning point doesn't necessarily mean that you're going from positive to negative, but it does mean you're going from either increasing to decreasing or back and forth. Or vice versa. So here, let's start off with a parabola. Right now, am I increasing or decreasing? I'm increasing, but am I positive or negative? Quicker you answer. Yeah, thank you. We are negative. Say it like you mean it. Okay, so I'm still increasing. I'm still increasing. What just changed now? Now I'm positive, but I'm still increasing. I'm increasing. I'm increasing until I reach this turning point. Now, what am I doing? I'm decreasing, but I'm still positive. Continue to decrease, 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 and now I become negative. So know the difference between the two. I guess of the two, I would say increasing and decreasing might be more important. But just know the difference between the two. If you were to be asked what intervals, anytime you see the word interval, you're talking about the x. Like along the x-axis. If this is where the vertex is at, which looks like 4, at what intervals, and let's just use interval notation, which we're used to, at what intervals was this function increasing? From negative infinity until 4. And actually 4 is not inclusive, it wouldn't take a bracket, because at 4, when you turn around, you're neither increasing or decreasing. So you have to put a parentheses around that. You always put a parentheses around the infinities. There's no such number as infinity. And then when is this function decreasing? From 4 to negative. From 4, not to negative infinity. From 4 to positive infinity. Because it's talking about, when you talk about increasing or decreasing, you're talking about the x-axis, right? So the reason why this is negative infinity to 4 on the increasing part is if I had enough space, you know, from all the way over here from negative infinity all the way up until 4, the graph kept on going up. If you had enough space to see it, this would go all the way to negative infinity. But then one time if I turn around and come back down, as far as the x-axis goes, how long is it going to continue to go down? All the way forever to positive infinity. Now, what interval are we talking about x? Oh, I know what I was going to say also. Okay. So, in a parabola, you call a turning point a vertex. There's only one of them, so it's called a vertex. But now we're going to start shifting the verbiage and calling them maxes and mins. Anytime you have a turning point that goes from increasing to decreasing, that's called a max. Anytime you have a turning point so like here, if I look over here, this is a max. Anytime I have a turning point that's decreasing to increasing, that's called a min. But there's different types of maxes and mins. There are local max and mins, which are also referred to as relative. You see the word local or relative, that means the same thing. And then you have also what are called absolute maxes and mins. Look at this parabola. Is that vertex a max or a min? It is a max. But is there anywhere else, anywhere on that parabola that goes above that? Huh? No, there is not. There is no point higher than that anywhere on the parabola. So this is an absolute max. This max is absolute. Because there is nowhere else in that parabola that goes higher. But now when I come over here to this cubic function, this first turning point up here, oh, I already told you it's a max. Is that an absolute max or is that a local max? Well, is there anywhere else on the graph that is higher than, how about max? Is there anywhere higher than this point right here?
Yes.
Yeah, sure. This part of the graph over here goes beyond that. And actually, I would continue on to infinity. So because there are other places on the graph that are higher than that, you can't say that that's a maximum value, so you would call that a local max. Or if you don't call it local, what other word might you see? Relative, yeah, relative local. Don't get confused by that. Down here, since I'm going from decreasing to increasing, that is a minimum value. It's considered to be a minimum. But is there anywhere else on that graph that is lower? Yeah, there is over here. This part over here is below that. This would also be. When a graph goes forever in a direction, it does not have an absolute. For instance, this goes forever down. This does not have an absolute limit. It would go all the way down to negative infinity. On this end, the graph goes all the way up. It does not have an absolute max. This first one, the parabola, does have an absolute max. Does it have an absolute min? Why not? Why does it not have an absolute min? Because it'll go down forever, yeah. The only way that you can have an absolute max or min is if your end behavior is in the same direction. If I had a graph that did this, let me erase some of this stuff. Let's just draw. What type of a turning point is that? It is a min because it's a down to up turning point. But is there anywhere lower on the graph? Yeah. So this is a local min. What type of a turning point is that? Local. Local max. Why local max? Because there's other places that are higher than that. It's an up to down turning point, so it's a max, but it's a local one. What type of turning point is that? Yeah, that's an absolute min. That's the lowest place on the entire function. That's an absolute min. Does this graph have an absolute max? The one I just drew in red, does it have an absolute max? And it is not a number. If something goes to infinity, there is nothing absolute about it. So one last thing on this slide, let's go back over here and let's talk intervals. Let's go from left to right. Under which intervals is this function increasing? Okay, definitely from negative infinity, because if I go from left to right, so all the way from negative infinity up until a certain point, I'm going up. So go from negative infinity to where? Where do I stop going up? At -2. Am I going up anywhere else? Huh? Well, I haven't talked about decreasing. Let's just stick to increasing. Are there any other intervals on this function where I am increasing? Yeah. After I start going down, eventually I'm going to turn around again and start going up. That occurs at 2, so it's a union from 2 to positive infinity. Do I have any intervals where I'm going down, where I'm decreasing? From -2 to +2. Maybe not as important, but just so that you don't get confused with -2. Under what intervals is this function negative? So now I'm not using words like increasing or decreasing, words like positive or negative. Well, you just kind of, you don't have to actually draw one, but you would imagine a line here. Under what intervals is this negative? Yeah, so negative infinity, let's just assume that we knew it's hard to tell because it's in between -3 and -4, but let's just say roughly between negative infinity up until like -3.5 roughly. It's negative. when does it become negative again?
0 to 0 to.
Yeah, from roughly, roughly from about 0 to a positive 3.5, it dips below that line again. When is this function positive?
Negative.
It would be, no, it's about negative 3.5 again. We're guesstimating there from about negative 3.5 up until 0. It's above that line. And then when does it become positive again? From a positive 3.5 up to positive, it stays above that line. So know the difference. I know Khan Academy asks the difference between the two. Be aware of the difference. All right, let's move on here. Analyze the intervals of increase or decrease. Let's go from left to right. As we go from left to right, are we initially increasing or decreasing? Yeah, first we're going down. This is a roller coaster. And funny enough, the path we're going to do this unit involves a roller coaster. So initially we're going down. So we're decreasing from negative infinity up until when do we turn around? This thing was hand drawn, so let's just assume this happens here at this point. Let's just assume it's a little bit off, but what point would that be? Yeah, -5. Okay, then we turn around. Once we turn around, now we're increasing. So that means we're going to be increasing from -5 up until when? Let's assume that happens like right around here. Up until when? -2. Okay. Then we turn around again. Now the roller coaster is going back down. Until when are we going back down? From -2 until +3. I ran out of space, so it should matter because I'm getting increased. So and then now here at 3, once I turn around, how far am I until when am I increasing? So from 3 to +3. If I know it doesn't ask you, but I want to emphasize it. If I were to ask you under what intervals is this function positive? I wanted to know when this is positive, under what interval is it positive? Not increasing or decreasing, under what interval is the function positive? Where is that function above the x-axis? If you go from left to right, it's from -infinity, and when does it stop being positive? When the first time it starts, like here, look, maybe since you're half asleep, maybe let's word it this way, right? What changes whether a function is increasing or decreasing? Turning points. Every time you hit a turning point, now you are no longer increasing or decreasing in the other one. What changes whether a function is positive or negative? X-intercept. When you cross the x-axis. So if I start off from -infinity, up here I'm above the x-axis, but eventually when do I cross the x-axis? That looks like a -6. Okay? But then I dip underneath from -6 until when? Yeah, it's a hand-drawn thing. It looks more like -3. Let's just say -3.5. May not be exact, but -3.5. Then we come back above at 3.5, or sorry, -3.5, until when? When do we finally cross the x-axis again? 0. At 0. Then we become negative again. But we become negative from when? From when to when? Yeah, let's just say for argument's sake, that was right there on that point. So from 0 to 5. From 0 to 5, we're negative. And then finally we cross the x-axis again. And we are positive from when to when? 5 to. From 5 until? Positive infinity. Increasing, decreasing, and positive and negative. Okay, this we talked about already, so we can skim through this really quick. Maximum and minimum. maximum, just the word maximum by itself means the highest point. We're talking about the y value, what y goes up and down. So maximum will be as high, like what's the highest you go. Minimum would be what's the lowest you go. And we talked about the difference between absolute and local. A local max or min is basically just a turning point. You can add this. If you see relative or local max, those are just fancy words. Now, a turning point could also be absolute if that just happens to be the highest or lowest point on the graph. What type of a max is that? Local. What type of a min is this? Also local. All right. So here's a graph. Let's identify an absolute max, a local max, an absolute min, and a local min. This might have already been written. I think half on time. Does this graph have an absolute max? It does. Where? Does this graph have an absolute max? No. Does this graph have a local max? Yeah, it's got two of them. I don't have a graphing utility, so I study on your paper. What that person, the one that really thinks that 0, 1, and 210. Okay, so they're saying that it's right here at 0, 1, and then 1, 2. That's. It looks like part of this was a computer image, and then this last little section was hand drawn. But let's just say that even if it's let's call it a sketch. Like yesterday we were calling it graphs and sketch. Let's say this were a sketch. Can you suspend disbelief and just assume that this point here is at 0, 1, and this point is at 210? Can you assume that without getting confused? It's close enough, kind of thing. And just more important thing is that you know what a local max looks like. Does this graph have an absolute min? Yes, how many? Just one. Absolute only has one. Absolute has to be the lowest point there. I can't tell from the drawing what do they put for the absolute min. I don't get the wrong one. Oh, they put y equals -8. Let's just say that's I don't know. Yeah, let's say -1, which what would kill that is the thing is that they've already given us the function, so I'm pretty sure if you plug in a -1 there, you're not going to get -8, but let's kind of also pretend that they didn't. This is not the most important thing for me right now. So like pretend that this isn't even there. Let's just only look at the graph. Do we have any local mins? Yeah, which one? There's one here which it's hard to tell, but let's just see. Well, actually, yeah, there's two. You're having to do this one also. So it's already written on your paper. For some reason, they put 1.5. I guess they would say. Now, you know what I could have done is I could have put that on with decimals, and we would have gotten the exact point. But I care more just to what they look like as opposed to actually calculating it. We're not going to use graphic calculator much in here. 5, 6. So what they're telling you is that this point here is at 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Any questions there? You all right, buddy? All right, domain and range. This we should be used to. What does domain mean? What does domain mean? Quicker you answer, quicker I finish, less you have to hear me. What does domain mean? Let me put all the possible answers. On a parabola, you should have learned algebra 1. What's the domain of all parabolas? All real numbers here. Parabolas go forever to the left, they go forever to the right. Range is what could be affected by turning points. So like if I look at this parabola from left to right, I'm starting to decrease. I'm going down. I want to make it to negative infinity. Oh, I just turned around. So how low does this graph go? Yeah, -7 would be the absolute mean here. Now we actually do touch -7, so this will take a bracket. And then how high do we go? Domain and range, what's the domain of any parabola? Every parabola is going to have pretty much, I didn't even take it a step further, pretty much any polynomial function, even if it's not quadratic, it's going to have a domain of all the numbers. It's the range that could be affected, or that could be limited. What's the range here? How low do we go here? Another problem with range is that our eyes are trained to scan documents in two directions. We are used to going from left to right, so domain isn't that big of an issue. But when it comes to range, like when you read a sheet of paper, you go top line, the next line, the next line. We're used to scanning a document from top to bottom. So when we talk about range, your eyes are trained to look at it from the high end to the low end. But intervals are always supposed to go from least to greatest. So in range, if you're going from least to greatest, it should be from the bottom. So we go to negative infinity, and how high do we go? Yeah, that looks like 5. And we do touch 5, so 5 will carry a bracket. Okay, increasing and decreasing. So let's talk about max min, let's talk about intervals, let's talk about range. But what's the first type of max or min that we see? That we go from left to right. What's the first type of max or min that we see? A local what? Yeah, there is a local max. And that is at -322. Are there any other types of maxes there? No. We do have also a local min that appears to be at 3 -14. We have a local min at 3 -14. Do we have any absolute maxes in this? No, because we both go forever up and forever down. Okay, I'm going to assume for intervals here, we're talking about increasing or decreasing. Are these also frequent in the paper? No. So we're not talking about intervals here for positive, negative. We're talking about intervals of increasing and decreasing. What did I tell you? See, if I didn't have Candy already, this would be a question here. Who was listening? What do intervals of increasing or decreasing depend on? No, not yet. No. Positive and negative. Positive and negative depend on x-intercepts. Every time you cross the x-axis, that changes if you're positive or negative. It does not change if you're increasing or decreasing. What changes the fact that you're the turning. So if you are increasing, you will continue increasing until you reach a turning point. If you are decreasing, you will continue decreasing until you reach a turning point. If you go from left to right, does this start off increasing or decreasing? It does start off increasing. And so when do we start increasing? When did this graph start increasing? From negative infinity until when? Until what? 22, not until 22. We're talking about intervals, we're talking about the x. So until -3. Then we turned around and we started decreasing from 3 until when? Until positive 3. Then we turn it around again and we increase from 3 until positive 3. Lastly, domain and range. What's the domain of this polynomial function? Yeah, this will go forever, left, forever, right, so there's no real numbers. Negative infinity, positive infinity. How about the range here? Yeah, because I do have an arrow going up and an arrow going down, this will go forever down and forever up. But, I know you may or may not know this yet, but like this particular shape of a graph is cubic. And you see this kind of go up, go down, go up, or go down, go up. If you were to also see it go down, go up, and then go down again like that, those are cubic. Any type of odd function should have both domain and range be forever. Like what type of odd function or odd degree function are you most used to? What type of odd degree function are you most used to? Linear. Okay. And when you have lines have infinite domains and infinite ranges both. The same thing applies to other line behavior. What are the arrows doing? Odd degree functions will do the same thing. You have one arrow up, one arrow down. Are you hyper-focused or hyper-bored? Okay, so for each, let's match the equation to the graph. All right. If you want to do well on that quiz on Friday, I would pay attention to these. I know there's some that are like this. First thing I would look at is end behavior. But if you look at all these choices, they're all exhibiting the same end behavior. What is it? Up and down. Yeah, they're both exhibiting up and up end behaviors. All three of them are. So that's not going to help you. Now, what type of function would exhibit up and up end behavior? In order for there to be up and up end behavior, positively and odd. Not odd. And even degree, but that's not going to happen with all of them. Should be positive and even degree. What I would say is it's going to have to be the x-intercepts here. And also the multiplicity, what's happening at that point. So here, this first one, I should be crossing the x at 0, at -4, and at +6. At 0, my multiplicity is 1, so I should be going straight through. At -4, my multiplicity is 5, so it should flatten out and then go through. At 6, my multiplicity is 8, which is even, so it should bounce. It should start using better words now. TP for toilet paper. No, just kidding. It's a turning point. So 6 should also be a turning point. Which one of these graphs is touching at 0, -4, and at 6? Where at 0 we're going straight through. At 6 we have a turning point, and at -4 it's getting flat and then going through. Well, yeah, there's only one that touches at even at 0. The 3 is the only one that I see that in. That would be B. Yeah. This next one, we're touching at -3, at 4, and at 9. At -3, the multiplicity is 7, so that's going to be flat and then through. At 4, it's even, so there's going to be a turning point. And at 9, the multiplicity is 1, so that's just going to go straight through. Which one of these is exhibiting that type of behavior? C. Yeah, it doesn't look like C. It's the only one that goes out to where 9 will be it. So this would be C. Okay. Questions there? Let's see this. The area of a rectangle can be found using this equation. Express the area as a sum or difference of mononomials. Alright, this is just a fancy way of asking you to do what? Definitely not long division, no. Right now, when you have two parentheses, what operation are you being asked to do? Multiply. But if you want to only have the sum or difference of monomials just means a term. If you want to see what term is being added and subtracted, I mean, I don't want to multiply. I want to get rid of the parentheses. How would I get rid of the parentheses? It starts with full and ends with ill. Very good. Thanks, Haley. Stephanie was about to say that, but then she didn't say it. So this would be x to the third plus 4x squared plus 5x squared plus 10x minus x minus 2. Two x to the third plus 9x squared plus 9x minus 2. The volume of a box can be expressed by that. Expressed by the difference of as a sum difference of monomials. What do they want you to do here? Yeah, to simplify that. Here, I'll let you guys do that on your own, and then I'll do it afterwards. I'll give you like a minute to see if you can do that on your own. Post that. Go. Alright, so I gave you a head start. Now this is going to involve both FOILing and distributing. I like to distribute after. This is my personal preference. So this function is called v of x. I would use the x alone and FOIL first. But it's up to you. Like we should have gotten still the same answer even if you didn't do it in this order. Minus 20x minus 3x FOIL of x squared. I would combine the like terms and take the opportunity to write this in standard form, not because you have to minus 1. If I'm going to take the step to combine like terms, I might as well also write this in standard form. And then if you haven't noticed, anytime you distribute just an x, what's going to happen? Each degree goes up by 1. So x to the third squared plus 5x. Or is that what you got?
Yeah.
Have a good week of managing.
Oh, good.
Are you looking forward to the extra hour of sleep this weekend?
Yes.
Alright, describe the end behavior of each function. So some of these are graphs and some of these. This is kind of getting to the review portion already of the packet. I did look at the quiz for Friday. You need to know arrow notation, so let's just do it in arrow notation. We could verbally say like up and up, down and up, but let's write it in arrow notation. When you're given the function, not the graph of the function, but when the function is written, what does that depend on? What determines that behavior? The lead term. Here the lead term is x to the third. So what's my end behavior going to be? If I have a positive lead coefficient with an odd degree, what's my end behavior? Could be down and up. Left arrow down, right arrow up. How would I write that in arrow interfacing? As x approaches negative infinity, which that's my left arrow, and when x approaches positive infinity, that's my right arrow. What's happening if I say down and up? What's the left arrow doing? If I say down and up, what's the left arrow doing? Going down. So f of x will also be going negative infinity. If I say down and up, what's the right arrow doing? Going up. What you see on the board. But it's not matching. These are just different questions. Okay. Now we move on to number 2. And number 2 is going to ask the same thing for end behavior, but instead of giving us the function, they give us the graph. Now it's a little bit easier because you just look at it. What end behavior is this exhibiting? This is up and down end behavior. So now let's write that. We're always going to have an x going to negative infinity, which that just means left. We're always going to have an x going to positive infinity, which that means to the right. Right now, let's see what f of x is doing. Y. What's the left arrow doing here? This first one means x going to negative infinity means left. X going to positive infinity means right. What's the left arrow doing? It is going up, so that means that f of x is going to positive infinity. What's the right arrow doing? Going down. Go to the next one, number 3. What's the lead term here? Can you see it on your paper? Just see it on your paper. It's negative x to the third. What end behavior is exhibited when you have a negative x to the third? If it's a negative lead with an odd degree, it's up and down just like number 2. It's up and down to number 2. So you know what happens when x goes to negative infinity, then you know what happens when x goes to positive infinity. If you're half paying attention right now, look, every single one of these is going to start off looking like that. Like I could pre-print this as a template, and every single one you're going to start like that. What's going to change is what happens with the y. So first off with the left arrow, what's the y doing with the left arrow? You just told me up and down. The left arrow is the one that goes up. So positive infinity. What's the right arrow doing? Going down, negative infinity. We'll get through as much of this page as possible, and we'll leave the last 6 pages for tomorrow. So, how about number 4? What type of end behavior is being exhibited on number 4? Up and up. That is up and up. I could, if I wanted to, I could pre-print on every single one of these. X goes to negative infinity. What does f of x doing? As x goes to positive infinity, what is f of x doing? And if they're both going up, what am I going to put next to each of the f of x's? What am I going to put? Positive infinity, positive infinity. For number 5, what's the lead term? Positive x to the 5th. So that's a positive lead with an odd degree. What's the end behavior? Down and up. I can go ahead and write x going to negative infinity. I can write x going to positive infinity. I want to know what f of x is doing. If the end behavior is down and up, what's the left arrow doing? It's going down, which means it's going to negative infinity. What's the right arrow doing? going up, down and up in behavior. What type of behavior is number 6 exhibiting? A behavior. They're both going down, so I could go ahead. Even like before I said a word today, you could have walked in here with this already saying x going negative infinity. What is f of x doing? As x is going to positive infinity. What is f of x? Like this could have already been printed on your paper. You could have written it in, and now we just got to fill in what y is doing. And if both arrows are going down, negative infinity, negative infinity. Number 7. A negative with an even is down and down, so it's going to look the exact same way that that did. So x is going negative infinity, f of x is going also, f of x is also going to negative infinity, as x goes to positive infinity, f of x is also going to negative infinity again, but both arrows are going down. Finally, on number 8, what end behavior is here? Down and up. So as x goes to negative infinity, what's f of x doing? Also going to negative infinity. The last arrow is going down. As x goes to positive infinity, what's the f of x is also going to positive infinity. Tomorrow we'll finish the rest of the packet. Should be able to get through pretty much all of it. And then what do we do Thursday? Lab on Thursday and Friday. It might be better.